Welcome friends. We are discussing network solving techniques. In the last few sessions we have discussed different theorem, their philosophy and few problems on them. Now we have remained only one theorem, that is Norton's theorem. It is also a very important one. Now, philosophically, it is quite similar to Thevenin's theorem, except few points. The mathematical flow very similar. The mathematical flows between Thevenin's theorem and Norton's theorem are very similar, except few things. So we shall see them in details. So we shall have Norton's theorem to discuss. Now, the statement is very similar, except this point that now suppose in case of a Thevenin's theorem, okay, let me find out the steps that were this. Okay, so that in case of a Thevenin's theorem we have discussed this, by this example. Now in case of a Norton's theorem we try to understand what are the different steps. Let us say we have same example, same network, and we want to calculate current flowing through the RL. So the first step for Thevenin's theorem to open circuit RL and to measure or calculate V Thevenin. Now in case of Norton's theorem, the step number 1 is short circuit the load short circuit the load resistance RL and to make or to measure or calculate I short circuit, which is also called IN, that is Norton's current. So IN essentially stands for Norton's current. So let me figure out. It was our actual diagram network. We have V1, then we have R1, then we have R, right? Then we have R2, then we have V2. Now the first step of the Norton's theorem is just to make short circuit of the load resistance. Unlike the Thevenin's theorem, in case of a Thevenin's theorem it was the open circuit, but in case of a Norton's theorem it should be short circuited. The load should be short circuited by this. This is IR1, this is, and we need to make this RL is short circuited like this. Now as the you know, this resistance is shorted, this R resistance is shorted, so all currents will be flowing through this short circuited path because this resistance is bypassed. And let us say this short circuit current is IN or ISC. This current is called Norton's current or Norton's equivalent current. The second step is same with Thevenin theorem, that is to calculate or measure RTH. To measure or calculate RTH. It is same. Now with respect to this problem, as already discussed, RTH will be is equal to R1 parallel R2. It is already discussed in the Thevenin's theorem. Now third part is the just like the Thevenin's theorem, Thevenin's theorem, it was Thevenin equivalent network. Now in case of Norton's theorem, you need to construct Norton equivalent network. Norton's equivalent network. What is that? You must connect your Norton current. You must connect your Norton current IN in parallel with RTH, and also with that parallelly your R will come, that is load resistance will come. So this current flowing through the R will be calculated by the principle of current division rule, that is total current into resistance of the other branch, which is RTH in this case, divided by summation of two resistances RTH plus R. So this is the philosophy of Norton's theorem. So in case of Thevenin's theorem, we open circuit the load. In case of Norton theorem, we short circuit the load. Both the cases, load resistance is effectively off, effectively out of the network. One by making open circuit, another one by making short circuit. The second step, which is RTH, is exactly same. Now third one is the Thevenin equivalent resistance, which is a Thevenin voltage in series with, you know, RTH and RL, and in the Norton equivalent network it is Norton current in parallel with RTH and R. So now if I keep two networks side by side, you will observe a strange similarity. So this is your Thevenin equivalent voltage, Thevenin equivalent network. ETH, RTH and R. Let us mark these two extra nodes X and Y, and IN in parallel with RTH. Then we will mark the same two nodes XY. Then we have R. So if you look closely, this part, so with respect to X and Y terminal, you will get a strange relation that is nothing but your IN. Now if you follow the source conversion technique, your IN should be is equal to ETH by RTH. Similarly, if you follow the same technique, your ETH should be is equal to IN into RTH. So that is why Thevenin's theorem, Norton current and Thevenin resistance is related with this relation. Thevenin voltage is equal to Norton current into Thevenin resistance. You see, this is, you can get this relation. There is very strong relationship between these two networks, Thevenin equivalent network and Norton equivalent network, by source conversion technique. If a voltage source is connected in series with a resistance, then same assembly can be converted to a equivalent current source with the parallel with that resistance. So IN is nothing but ETH by RTH and vice versa. So going to the topic now, statement, it is same statement as discussed. The first one is the general statement. It is for a linear active bilateral network. Alright, so then a current source in parallel with the resistance and load resistance, it is represented. So the current source is called Norton equivalent source, as already explained. It is called short circuit current. The Thevenin resistance part is already explained. Now construct Norton equivalent circuit as shown in figure 19, this diagram. So by current division rule, we can get this result, that is IN into RTH over RTH plus RL. So let us solve one problem on Norton's theorem. Let us consider figure 20, where you have to find out is it the same thing, or is it, I hope it is the same as that of seen in the Thevenin's theorem. Yeah. So not same actually. This 5 ohm is added additionally. This 5 ohm resistance is added additionally. So anyway, so you need to find out the power loss in 10 ohm resistor. So this is again your load resistance, 10 ohm. So through this you first find out the current flowing through. From there you must calculate the power loss in this 10 ohm resistance using Norton's theorem. So once you redraw the circuit, the step 1, which is this one actually. Let me draw the circuit again. This is 1 ampere current source. This is 2 ohm resistor. Then we have a 5 ohm resistor. Then you have a 10 ohm resistor. Then you have a 5 ohm resistor again. Then you have a 10 volt source. Now you must make this RL is shorted, so you must make it first this one as a short circuit. So this current is IN. Now first you need to understand some aspects of this network. You need to analyze. Since these two nodes are shorted, see this node and this node is shorted. So basically you see this node is at ground potential So since these two nodes are shorted, so this ground potential node is actually becomes this one, because now difference between this node and this node. For the figure 20, this node X and Y are different because there is a potential difference in this 10 ohm resistor. So that differentiate between node X and node Y by some amount. However, as the 10 ohm resistance is short circuited, by short circuiting we mean that 10 ohm resistance is effectively out of the network. So that means this node X and this node Y becomes now they are now same node actually. So the potential of X becomes now this 0 volt because it is short circuited. That is the reason. So current flowing through this 5 ohm resistor is 2 ampere. Current flowing through this 5 ohm resistance is 2 ampere. And this current flowing through the 5 ohm resistance is by 7 ampere. Now why? What is the reason? Let me solve one by one. So the potential of, so let me write down one equation at a time. So you see this is short circuited, so node X becomes now the ground node. So we write the KCL at node X. We write the KCL at node X. So it is written this current is in this direction. So the polarity of the 5 ohm is like this. So we have, the written is 10 minus, the current is 10 minus Vx by 5. 10 minus Vx by 5, that is entering. This current is also entering from Z to X. So that is why I have written IZX. And this current is leaving, which is IN. So that is IN is written here. That is equation 9 for you. Now what is IZY? What is IZY? This current IZY. IZY is nothing but, there are two paths, as I have told you, this node is 0 volt. So effectively this 1 ampere current after reaching at node Z, it is getting two paths. One is along this, another one is along this. So IZY, it is written, it is the current division rule, that is total current, which is 1, into resistance of the other branch, which is 5 ohm, divided by summation of 2 plus 5. So it will be 5 by 7. And similarly IZX, the same way we can evaluate IZX, by the same way we can evaluate 1 into 2, that is the resistance of the other branch, divided by 2 plus 5. So it will be 2 by 7 ohm. So that is why I have mentioned this current as 2 by 7 ohm. And this current is 2 ampere because this is 0, so this volt is 10. So the potential difference is, 10. So 10 by 5 is 2 ampere. So from here we can write 10 minus 0 by 5. So from this equation, actually it is the continuation of equation 9. So 10 minus 0 by 5 plus 2 by 7, which is IZX, it is equal to IN. So IN is nothing but 2 plus 2 by 7, which is equal to 16 by 7 ampere, which is equal to 16 by 7 ampere. That is your Norton current. Now in order to calculate RTH, let me draw again circuit. So we have a 5 ohm resistor, then 2 ohm resistor, then we had a current source, then we have a 5 ohm, then so this was actually our original circuit. 1 ampere, 10 volt. 1 ampere is the current source, 10 volt is the voltage source, and this resistance was 10 ohm, I think. Yeah, 10 ohm. So we solve one by one. So first of all, we need to look from the load terminal. So you need to sort it. Sorry, no, it is the Thevenin equivalent resistance. So that is why you need to look from here to measure RTH. That is the step number 1. This is RTH. Now how you can measure? You must remove voltage source by making it short circuit. So you must sort it. You must sort it. And by removing current source, how you can remove the current source? By making it open circuit. So let us make it open circuit. Let us make it open circuit. So with respect to X and Y terminal, there are two different paths. One path is along this 5 and 2 ohm, and another path is along this 5 ohm. So basically RTH, that is the Thevenin equivalent resistance, is nothing but 5 ohm parallel with 7 ohm. Because these 5 and 2 are effectively in series, so basically it will be 35 by 12 ohm. 35 by 12 ohm. So that is our RTH. Now let us construct the Thevenin equivalent network. Norton's equivalent network. So first we have Norton current, which is equal to 16 by 7 ampere. Then with that, parallel to 35 by 12 ohm, that is our RTH. And then we have a RL as 10 ohm. So this is the Norton equivalent network. So what will be I? Current flowing through 10 ohm resistance, it is the total current 16 by 7 into resistance of the other ones, that is 35 by 12, divided by summation of two resistances, that is 35 by 12 plus 10. So if you calculate or if you solve, the numerator will become, this is 5, this is 4, this is 3, so numerator will become 20 by 3, and the denominator will become 155 by 12. So 20 by 3 by 155 by 12. So it will be, I think it will be 16 by 31 ampere. So what will be the power loss if you solve 16 by 31 whole square into 10? So if you solve this, it will get 2.66 watt power. So with this example, we have shown or we have illustrated the example on Norton's theorem. First, we sorted the 10 ohm resistance and we have evaluated Norton current, that is 16 by 7 ampere we get. Secondly, thereafter we have evaluated RTH, which we have already done in case of Thevenin's theorem once. So by following the similar procedure, we have measured RTH from the load terminal, as it can be shown here. So it is 35 by 12 ohm, and once we got RTH and IN, we have constructed Thevenin equivalent, Norton equivalent network, that is IN TH and RL all connected in parallel. From there we have solved current flowing through 10 ohm resistance is 16 by 31 ampere, and from there we have evaluated power loss is 2.66 watt. So with this we have discussed all the theorems starting from Thevenin's, Norton's, superposition theorem and maximum power transfer theorem. So here we conclude the module 4. In the next module, module 5, the module 5 will also be discussed or will be full of these topics with some more problems like AC networks and dependent source and stuffs like that. So we will solve more problems on those theorems, KCL, KVL, node analysis, mesh analysis in the next module. And the more you practice, more you solve on these network problems, the better you will grab the practice of solving network problems. So with this I am concluding here. So module 4 is we are ending module 4 here. So we will shortly discuss module 5 from the next session. Thank you.